Okay, let's continue. Powers of rationals. Consider a rational A. We can ask, can we take powers A power n where n is an integer? So note that we have this sequence. If you multiply a power 1 by a, you get a power 2. If you multiply a power 2 by a, you get a power 3, and so on. So we have this sequence. We want to define a power minus negative powers 0th power such that, so we want this picture to hold. Into a gives a power minus 1, into a gives a power 0, into a gives a power 1, gives a power 2. We want this picture to hold. Hence we define a power 0 equals 1, a power minus 1 equals multiplicative inverse of a power minus 2 is a power minus 1 times a power minus 1, a power minus 3 is a power minus 1 times a power minus 1 times a power minus 1, and so on. So with these definitions, so I'll let F. So with this definition, the above picture will hold. Right? So hence we define a power n equals taken n times, a power 0 equals 1, and a power minus n equals the multiplicative inverse of a taken n times. For positive integer n. So we have defined powers of rationals, non-zero rationals. Okay, consider rational A. Here we need to take a not equal to 0. This is a crucial thing I missed. So otherwise the multiplicative inverse won't exist. So can we take powers a power n where n is any integer? Yes, we can take powers a power n where n is any integer, like so. Right, an example. 2 power minus 5 is by definition multiplicative inverse of 2 take multiplied 5 times. This is 1 by 2 power 5, 1 by 32, right? Another example, 2 by 3 power minus 5. This is the multiplicative inverse of 2 by 3 taken 5 times. Multiplied 5 times with itself. So this is 3 by 2 power 5. This is 243 by 32. So we can take any integer power. We can raise a non-zero rational to any integer power. Okay. An example. A chemical substance disintegrates in such a way that it gets halved every 10 minutes. If there are 20 grams of the substance present at a given time, how much will be left after 15 minutes? After 50 minutes. So in the beginning there is 20 grams of the substance. After 10 minutes it gets halved, so it becomes half into 20 grams. After 10 minutes it again gets halved, so you get half into 20 grams. And so on. Hence after 50 minutes is 5 by 8 grams of the substance left. Hence after 50 minutes there is 5 by 8 grams of the substance left. So this is one natural situation in which the powers of half appear, right? And here the chemical disintegrates in such a way that it gets halved every 10 minutes. So after 50 minutes it becomes half of half of half of, so on. You need to take half 5 times. So 1 by 2 power 5 times 20 grams, which is 5 by 8 grams, right? So let's continue. Note that an equation of the form Bx equals A, where B are rational, B not equal to 0 has a unique rational solution. X equals A by B. So consider equations of the form x square equals A, where A is rational. So more specifically, consider the equation x square equals 2. Does the equation have a rational solution? Consider the equation x square equals 2. Does the equation have a rational solution for x? So let's see. The observation is this equation has no rational solution. So we saw that within rational numbers, we can solve equations of the form bx equals a, where a and b are rational. The solution is found by dividing the two rational numbers. Now consider equations of the form x square equals a, where a is rational. Can we sort of solve these kinds of equations? Can we find a rational whose second power is a? Or more specifically, can we find a rational whose second power is 2? Observation. X square equals 2 has no positive rational solution. Hence, it also doesn't have any negative rational solution. That is, it doesn't have any rational solution. So x square equals 2 has no positive rational solution. We cannot find a rational x such that its second power is 2. So proof is, let x be a positive rational solution. We can write x in lowest form, right? So we can write x as m by n, where m and n are positive integers and 1 is the only common divisor of m and n. So hence, since x is a positive rational solution of x square equals 2, we have n square equals 2. Multiplying by n square both sides, m square equals 2n square. Hence m square is congruent to 0 mod 2. Hence m is congruent to 0 mod 2. So we already saw while discussing congruences that yeah, if a square is even, then a is even. If a square is odd, then a is odd. Hence m square is even, m square is 0 mod 2, hence m is even, that is m is 0 mod 2. So hence m equals 2m dash for some positive integer m dash. Hence m square equals 2n square. So this equation, so this m square equals 2n square, this becomes 2m dash square equals 2n square. that is m dash n square equals 2m dash square. Hence n square is congruent to 0, even n square is congruent to 0 mod 2. Hence n is also congruent to 0 mod 2. So we saw that both m is congruent to 0 mod 2 and n is congruent to 0 mod 2. This is a contradiction. Hence, so m is congruent to 0 mod 2 and n is congruent to 0 mod 2. Hence, so we are writing this equation m square equals 2n square. This becomes, after substituting m equals 2m dash, this becomes n square equals 2m dash square. Hence n square is 0 mod 2, hence n is also 0 mod 2. Hence 2 is a common divisor of m and n. But we defined m and n such that x equals m by n is in its lowest form. A contradiction. Note that x equals m by n is in its lowest form, or I'll just write m by n in its lowest form. A contradiction. Hence x square equals 2 has no positive rational solution. So x square equals 2 has no positive rational solution. If at all it had some positive rational solution, we got a contradiction. So x square equals 2 has no positive rational solution. Now let's continue. Consider the number line. Is every point on the number line a rational number? So the answer is no. Consider, so is every point on this number line? So if you pick any point, can we express it as a rational number? So the answer is no. Consider this point, the point x. So it's constructed like this. You have the number line, you have 0, you have 1. Take a right angle triangle. This length is also 1. And then consider this length of the hypotenuse x. And then take a circular arc, and the point where the circular arc meets the line, you call that point x. Right? Consider this point x. Now suppose x is rational. So by Pythagoras' theorem, which we'll discuss later, suppose this point x is rational. That is, the hypotenuse of this right angle triangle is rational. Then by Pythagoras theorem, we have square of this rational number x is 1 square plus 1 square. That is x square equals 2. But box square equals 2 has no positive rational solution. We saw that in the above observation that there is no rational number whose square is equal to 2. But box square equals 2 has no positive rational solution. Hence a contradiction. So we assume that suppose x is irrational, then we got a contradiction. Hence the point x is not a rational number. So we have found a point on the number line which is not a rational number, which is not expressible as m by n, where m and n are integers and n is not equal to 0. So we have found this point successfully, this point, by looking at the hypotenuse of the right angle triangle with side lengths 1. That length is not a rational number. Supposing it is a rational number, we have that the square of the rational number is 2, but x square equals 2 has no positive rational solution. Hence this point, hence our initial assumption that suppose x is rational and then taking its square. So suppose x is rational, that assumption is false. The point x is not a rational number. So the answer to this question is, every point on the number line a rational number? The answer to this question is no. So the points on the number line which are not rational numbers are called irrational numbers. So here we crucially used by Pythagoras theorem. So this we'll show later. So this is a fact in basic geometry, that if we have we have not yet understood how to square any length, but we know how to square a rational length. We know how to do arithmetic with rationals so far. So assuming this length is rational, we can take the square, and then assuming the sides of this right angle triangle are all rational, we get this relationship between the side lengths, which is x square equals 1 square plus 1 square. So this is due to Pythagoras theorem. We'll look at Pythagoras theorem later. So we have crucially used Pythagoras theorem here in the construction of this point x. So what did we do here? We defined powers of a non-zero rational, and we have considered the equation x square equals 2. So this equation, considering this equation, naturally led us to finding a point which is not a rational number, which is not expressible in the form m by n, where m and n are integers. So x square equals 2 has no positive rational solution, and we could find a point x such that x is not a rational. Right. So that's all for this part. See you in the next part.